Hello students, today we're going to look at graphs of logarithmic functions, and in particular we're going to compare these to graphs of exponential functions. So what I want us to do is use a table of values to sketch two graphs. We're going to sketch the graphs of f of x equals 2 to the x, which we've already seen, and then g of x equals log base 2 of x, which will be new to us. So for f of x equals 2 to the x power, we can pick -2, -1, 0, 1, 2, and 3 for our x values. 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4, 2 cubed is 8. 2 to the negative first is 1/2. Remember, a negative exponent moves us across the fraction bar into the denominator. And 2 to the negative second is 1/4. So if we plot these points, we've got 0, 1, 1, 2, 2, 4, 3, 8, -1, 1/2, -2, 1/4. And we know what this graph looks like because, of course, we've already graphed it. We've already seen this. And we know that it has a horizontal asymptote for the x-axis. So it's getting closer and closer and closer to the x-axis, but never crossing it. So this is our graph of f of x equals 2 to the x. Now we want to make a graph of g of x equals log base 2 of x. And so it's important for our x values, to make things easy, for these to be powers of 2, because remember, the logarithm is asking what power do we need to raise 2 to end up with x. So in this case, it's actually useful for us to choose our x values to be 1/4, 1/2, 1, 2, 4, and 8, because these are all powers of 2, and that will allow us to take the logarithms easily. Let's actually start at the bottom and work our way up. If we look at log base 2 of 8, that's asking 2 to the what power is 8? And we know 2 to the third power is 8. So that's going to give us the point 8, 3, which is right here. Then if we look at 4, we're asking what power can we raise 2 to get 4? And we know 2 to the second power is 4. So this gives us the point 4, 2 on our graph. Then 2 to the what power is 2? The answer is 1. So this gives us the point 2, 1. Then 2 to the what power is 1? We know that 2 to the 0 power is 1. So this gives us the point 1, 0. Now if we look at 1/2, this is saying 2 to which power is 1/2? And we know that that's going to be -1. So this gives us the point 1/2, -1. And if we look at 1/4 for x, 2 to the what power is 1/4? Well, we know that that's -2. So this gives us the point 1/4, -2. And as we connect the dots, we get a graph that looks something like this. And our function is not going to go to the left of the y-axis, because if we try to take a logarithm of a negative number, it's not possible to raise 2 to any power and end up with something that's negative. So our graph is not going to end up crossing the y-axis, and in fact, our graph ends up being asymptotic to it. Now, if we want to see what the relationship is between these two graphs, we can quickly draw in the line y equals x. I'm going to do this as a dashed line. And we notice that our graphs are actually reflections of each other across this line. here we have our g of x equals log base 2 of x. And this should not be a surprise because I've told you that these are inverse functions. And we know that inverse functions have graphs that are reflections of each other about the line y equals x, which I'm realizing now I wrote y equals y, it's y equals x. And also, if we look at our tables of values, we can see that in our logarithm, we've just switched the x and the y values. So we've switched the inputs and the outputs. And so we can see that these are definitely inverse functions of each other. And this will be true even if we looked at a different base. If we looked at 3 to the x and log base 3 of x, if we looked at 10 to the x and log base 10 of x, we would still have inverse functions, and the graphs would still be reflections of each other. Now, I really want to quickly talk about domain and range before we move on. For our first function, the exponential function, notice that the domain is all real numbers, from negative infinity to infinity, but the range is only the positive numbers, from 0 to infinity, because this graph never goes below the x-axis. We know that when we look at a function's inverse, the domain and range switch. So in this case, the domain should be from 0 to infinity, and the range should be from negative infinity to infinity, and that's exactly what we have. If we look at this graph, it's only to the right of the y-axis, so the domain is only positive numbers, and the range is all real numbers because this goes infinitely far down, and then as it goes to the right, it's going to be growing and growing and growing, and getting bigger and bigger and bigger. It's going to be getting bigger slowly as it increases, but just like the square root function, it's going to continue to grow as x gets bigger and bigger. And all logarithmic functions, no matter what the base is, will have a domain from 0 to infinity and a range from negative infinity to negative infinity. The shapes will be a little bit different depending on the base, either steeper or less steep, but all logarithmic functions will have the domain and range in common.